In this video, we explore some ideas within Chapter 2. We're going to be looking at atomic symbols that are a way to summarize the subatomic particles that are present in an atom or an ion, see how a mass spectrometer works, and then jump down to some things that we want to begin to have in our memory banks, descriptions of polyatomic ions and acids. The progression of this particular chapter begins by looking at the work of Thomson, Rutherford, and Millikan. Next is this discussion of a mass spectrometer and how that's connected to isotope calculations, descriptions, and a way to summarize the subatomic particles that are present. And then a whole series of ideas where there's descriptions of molecules and ionic compounds. This particular video is summarizing or exploring some ideas near the start of the chapter and then bringing in some that are at the end of the chapter. If I look at how these particular ideas in the chapter stack up in terms of difficulty, the ones that are in this video are mixed. The mass spectrometer, the operation of the mass spectrometer oftentimes is one of the more difficult topics. The other ones, as far as describing subatomic particles, polyatomic ions or acids, are near the bottom. Students usually do pretty well at those. But what I'm putting in the thicker outline here, they're really important that as ideas that we will be using throughout the semester. So we want to become very capable at recognizing acids and polyatomic ions and also subatomic particles, having an understanding of the symbolism for those. Now, we've seen previously experiments of Thomson, Rutherford, and Millikan. Recall, for each of these, our objective, we want to know the scientist, how the experiment worked, and the significance of the experiment. So, which of these were leading to insights into subatomic particles? In a way, you could say all of them, but more specifically, Thomson's investigation of cathode rays was credited with leading to the discovery of the first subatomic particle, the electron. Rutherford's gold foil experiment is leading to a nuclear model and an understanding of where we would now have protons and neutrons found within the atom. When we're summarizing that information, let's show it here. So we have three subatomic particles, proton, neutron, and electron. We have two of them that have an electrical charge, protons positive, electrons negative. The plus one and minus one are increments of the fundamental amount of charge, 1.602 times 10 to the minus 19th coulombs. It's multiples of that. You notice within the mass, protons and neutrons have much greater mass than that of the electron. For symbolizing that, this would be a representation here for carbon-12, 6 protons. That's the atomic number shown in green. Number of protons tells you which element you're talking about. And then the mass is both protons and neutrons. So in this case, you must have both 6 protons and 6 neutrons. You can vary the number of neutrons and still have a carbon atom. Those are isotopes of carbon. So within here, we find that carbon-12 would have both 6 protons and 6 neutrons. Carbon-11, 6 and 5. Carbon-14, 6 and 8. So you would have different symbols than for the different isotopes. In this case, each of the examples, protons and electrons, are equal to each other. That's a neutral atom. What if the number of protons and electrons are different? Is that allowed? Absolutely. If it has a net positive charge, it's called a cation, and a net negative charge, an anion. You would get a net positive charge if you removed an electron, a net negative if you're adding electrons. Those would show up in this symbol as superscripts on the right-hand side. To explore this and have some fun with it, one resource that's useful is at the PhET website. Show the link there at the top. It's a PhET sim called Build an Atom. Within the Build an Atom, you can explore the relationship between the subatomic particles and the symbols. Within the Build an Atom sim, there's 3 different activities you can choose from. You can use this first one to choose various combinations of the subatomic particles. It matches it up with the different elements as they're found on the periodic table. You can play with that one. I think the simple one's a little bit more on the mark for where we need to be, where again, you can choose different combinations of subatomic particles. It's putting the protons, neutrons in the center region, in the nucleus, to keep track of them. And then here's the corresponding symbol that goes with it. Fun to play with. There's also this final game tab. Different representations of a description here for the atom, and then it's asking you about the symbol that would go with it. So in this case, I see 2 protons. It's getting the symbol helium. 1 neutron as well. Mass is 3. 2 protons. 2 electrons found outside of it. So I would say the charge is 0. All right, I guess the PhD got me through that particular question. Next one. Say mass is 2. I have 1 proton, no electrons, so the overall charge is +1. Excellent. Here's a question and a resource within the e-text on the same subject. So it says magnesium has 3 isotopes with mass numbers 24, 25, 26. Write the complete chemical symbol, including the superscript and subscript for each, and identify how many neutrons are in an atom of each isotope. If you already know how to do this, you can skip the video, but I'm going to play the video within the e-text because I think it does a good job if you're still a little shaky on figuring out how to answer these questions.
Magnesium has 3 isotopes with mass numbers 24, 25, and 26. A. Write the complete chemical symbol for each. And B. How many neutrons are in an atom of each isotope? Atoms of a given element can differ in the number of neutrons they contain, and consequently in mass. So we typically use a symbolic notation to represent them, similar to the one shown here. Interpreting this notation will allow us to determine the number of protons, neutrons, and electrons for an atom. The symbol of the element matches what is shown in the periodic table. The atomic number, which is also the number of protons, is indicated by the subscript. Because all atoms of a given element have the same atomic number, the subscript is redundant and often omitted. The superscript, called the mass number, is the number of protons plus the number of neutrons in the atom. We generally use the notation with superscripts only when referring to a particular isotope of an element. Now let's take a look at how we would write the symbol for the 3 given isotopes of magnesium. Magnesium has atomic number 12, so all atoms of magnesium contain 12 protons and 12 electrons, and we represent this with the subscript of 12 in the atomic symbol. We now need to complete the atomic symbol by placing the mass number as a superscript. The 3 isotopes are therefore represented by magnesium 24, magnesium 25, and magnesium 26. It is important to keep in mind that the isotopes of any given element are all alike chemically. Magnesium chloride that contains a magnesium 24 atom behaves for all practical purposes identically to the one that contains a magnesium 25 or magnesium 26 atom. The mass of an isotope is determined by the sum of the protons plus neutrons. We can use this to answer part B, where we are asked to determine how many neutrons are in an atom of each isotope, which is the mass number minus the number of protons. All of the magnesium isotopes have 12 protons. This means magnesium 24 has 12 neutrons, magnesium 25 has 13 neutrons, and magnesium 26 has 14 neutrons.
So let's move on and see if we can apply this information. So on the left here, I show the symbol for hydrogen 2. That's how I would say it. Hydrogen 2 is referring to the element of hydrogen with a mass of 2. It's neutral. I don't see electrically neutral. I don't have a subscript here on the right. So I'd say the protons and neutrons add up to 2. Must have 1 electron to go with the 1 proton. Total mass would be 2, and it has 0 charge. How about these other symbols? What would you say the name is called? And what combinations of protons, neutrons, electrons, mass, and charge are applicable? Take a second, stop the video, pause it, see if you can grab a piece of paper and fill in those details. Here's the answers for me. Okay, so this would be hydrogen 3, mass is 3. We see the difference there is because it has 2 neutrons instead of 1. We have something with a positive charge, something with a negative charge, because we have an imbalance between number of protons and number of electrons. Those imbalances, if it ends up being net positive, we call it a cation. Net negative, it's called an anion. So this would be a sodium 22 cation and a fluoride 19 anion. I'm beginning to introduce an aspect of the naming here. So this anion, instead of being the element fluorine, I'm calling it a fluoride anion. We'll look more at naming within this chapter. Here's another puzzle to put together. So this one has different combinations. I think in each case, it gives you enough information to solve for the missing values and also determine the symbols. So pause the video, see if you can answer them. Okay, here were my answers for each of them. So it's sort of like a Sudoku puzzle. As you go back and forth, it gave you in each case enough information to solve for the missing ones. So within these symbols, they're really just a form of bookkeeping to keep track of the subatomic particles that are present. Now, I've mentioned the subatomic particles as being electrons, protons, and neutrons. Said that you can have different number of neutrons, but the same number of protons. Is that really possible? How would we prove it? Well, there's evidence for that in a modern instrument called a mass spectrometer. Mass spectrometer came under the same research group as J.J. Thomson. And so when we begin to explore how it functions, I think you're going to see the parallels to it. So here's a description of a mass spectrometer from your textbook. It says the Cl atoms are first ionized to form, well, the Cl atoms are being introduced as a sample, and they're becoming Cl plus. So I would say they're becoming Cl plus cations. They're then accelerated through an electric field, and their path is deflected by a magnet. In this case, it's introducing Cl atoms. That is the sample, and those are becoming the Cl plus cations. You can do different samples. But this one's taking those particular atoms, and it finds that you have 2 different paths for those ions that is indicative of 2 different isotopes, chlorine 35 and chlorine 37 and chlorine 35 were those isotopes. Take a second, pause the video. Why do you think their paths are different? What is leading to them having different trajectories as they go through the mass spectrometer? Here's the textbook description for what's going on. So it points out that there are various designs for mass spectrometers, but they have some common features. First of all, the atoms or molecules that you test become gases. So they involve heating them up as needed, turns the sample into a gas. The next stage within that, they're going to become positively charged ions. Positively charged ions are called cations. The cations then enter into the magnet, and their trajectories then differ Their trajectories depend on both the charge and the mass. Different ions are being separated, in this case based on differences in their mass because they had the same charge. The two variables that are affecting the trajectory are the charge and the mass. This sounds awfully familiar to what we saw with J.J. Thomson's investigation of cathode rays. He's credited with discovering the electron because he identified a ratio involving its charge and mass, and he was deflecting it, after all, in electric and magnetic fields. You can see the connection between the two. In a way, it's also similar to Rutherford's investigation in distinguishing between alpha and beta particles. They were passing through the electrically charged plate. What caused them to have different trajectories? Well, whether they went up or down depended on their charge, but the degree to which they deflected, once again, was depending on a ratio involving their charge and their mass. So a mass spectrometer functionally is related to these previous experiments. The particular cations then, if you notice, after they pass through the magnet, reach the detector. A graph of the intensity of the detector signal versus the atomic mass is called a mass spectrum. Let's see the information and how we use that in the output. Here's the output that we would find if we were testing that sample of chlorine atoms. Two different isotopes, and it turns out that in nature you have more of the isotope with mass 35 than with 37. That's why you have a greater signal. How much greater? Well, if I divide it up, it looks like this reaches to about 5, and this reaches up to about 1.5. So you have more of chlorine 35 than you do of chlorine 37. If I turn that into percentages, 5 divided by 6.5 is about 75% chlorine 35 and about 25% chlorine 37. Different peak heights because you have different natural abundance for these particular isotopes in nature. I can combine those. I've got about 75% of the isotope with a mass of 35 and about 25% with a mass of 37. I'm combining the percentage with the corresponding mass, the percentage with the corresponding mass, adding those together. That's the average mass that one would find on the periodic table. So when I see these particular values, these are all weighted by the natural abundance and the isotopes and the corresponding isotopes. Here's a representative exam question on the topic. So it says, in nature, magnesium consists of 3 isotopes. This is what we saw in the earlier video. So if you take a sample of magnesium, introduce it into a mass spectrometer, and we're interested then in separating them based on mass to charge ratio, which of these would then be the output for a sample of magnesium? One piece of information, if we look to the periodic table, we know that the weighted average mass has to be about 24.3. So qualitatively, which one of these do you think describes the output for the mass spectrometer? Pause the video, share your ideas. Okay, so within this video so far, we've looked at the shorthand of atomic symbols that describe the subatomic particles that are present, the operation of a mass spectrometer. Let's close by introducing these two ideas, polyatomic ions and acids. Within your book, you'll find tables listing various cations. Notice they have positive charge, and anions, those have negative charge. Something is called a polyatomic ion when it's not a single atom but a group of atoms together. NH4 plus is an example of a polyatomic cation. In fact, if I look at this table, I only see one polyatomic cation. If I look over here for the anions, I have several polyatomic anions. CO3 2- would be the carbonate anion. SO4 2-, the sulfate anion. So for each of these, what I need you to do is memorize the polyatomic ions that are in bold. You only have one cation that you need to memorize, but you have several anions. I need you to memorize the name, the formula, and the charge. I need you to know that nitrate is NO3 with a -1 charge. I need you to memorize that phosphate is PO4 3-. So I need you to memorize the polyatomic cation and anions and memorize their name, formula, and charge. Another thing to memorize, I need you to memorize these common acids. I need you to memorize the name and the formula. We're going to be building on these ideas. These are ones that I'm sure you're going to be quite successful with, but don't delay. Make sure you have these in your memory banks. The sooner, the better, because we're going to begin using these ideas.